Good morning, students. Now, the next topic is iteration methods. Iteration methods based on second degree equation. Based on second degree equation. Okay, first degree equation already over. What are the methods? Secant method, regular Falsy method, and Newton-Raphson method. Now, iteration methods based on second degree equation. Here, consider a second degree equation. Consider a polynomial of second degree as f of x equal to a naught x square plus a1 x plus a2 equals to 0. Take this as equation 1, where a naught must be not equal to 0 to maintain the second degree. Here, what are the unknown constants? A naught, a1, a2 are arbitrary parameters, to be determined by three appropriate conditions. Three appropriate conditions. See, to get two unknown constants, we need how many conditions? Three conditions. Appropriate conditions on what? On function f of x, or on its derivatives, f dash x or f double dash x, like that. Okay, now the first method based on second degree polynomial is Muller method. First method based on second degree polynomial is Muller method. Okay, and let us see what is Muller method. It is the extension of secant method. It is the extension of secant method. And here, what is the extension of secant method means? In secant method, what is approximate root? How to calculate approximate root? By joining 2 points on the curve by a straight line, the straight line intersects x-axis at the next approximate root, right? That is why it is called chord method. Chord means line segment. Now it is Muller method means extension of secant method means over the curve take 3 points. 3 points gives always 2 degree polynomial, right? If I get to 2 points, joining 2 points I am getting straight line, joining 3 points I am getting a parabola type second degree polynomial. Then here, to get the second degree polynomial, we have to consider let three approximations. Let xk minus 2, xk minus 1, xk be the three initial approximations. Three initial approximations to the root, to the exact root psi, of what? F of x equal to 0. Then a0, a1 and a2 in equation 1 are determined by the conditions, So I need how many conditions to evaluate three constants a0, a1, a2? I need three conditions. What are the conditions? Are at each point xk minus 2, xk minus 1, xk, you express the function f of x. At xk minus 2, what is the function? Fk minus 2, f of xk minus 2. Simply the notation is fk minus 2. It is equal to a0 xk minus 2 square a1 xk minus 2 plus a2, right? This is, I will write like this, at x equal to xk minus 2. Next one, at x equal to xk minus 1, what is this becomes? The function value is fk minus 1, and if I substitute in the function on the right side, it is equals to this one, right? a2. And at x equal to xk, what is the expression becomes? This is fk equal to a naught xk square plus a1 xk plus a2, a1 xk plus a2. Take this entire as equation 2. Okay, now three equations are there. Okay, now eliminate a naught, a1, a2 from equation 1 and 2, from equation 1 and 2. Then see, the Muller's method is very big derivation of Muller's method is very big. Okay, I am shortening this, and first equation and second, this one, what is the first equation? F of x equal to a naught x square plus a1x plus a2. This is our first equation. From first and second equation, eliminating arbitrary constants, at degree level and intermediate also there, then what we have? The determinant of what? F of x square x1. Next one, in this one, fk minus 2 left side part, right side part is what? Xk minus 2 square xk minus 2 1, the quotients of the unknowns. Okay, next one, in the next equation, left side part is fk minus 1, right side the quotients of a0, a1 and a2. This is 1, and lastly fk and xk square xk1, and it should be equals to 0. This will come in linear independent dependent eigenvectors topic. To eliminate the arbitrary constants, or to find the values of arbitrary constants, we have to make the determinant to 0. And why we are including this first expression, equation 1? Because I have to get the polynomial first. That is why I have included this first expression, f of x square x1. Clearly, once again, f of x is left side of equation 1. Next one, x square is quotient of a0, x is quotient of a1, 1 is quotient of a2. Similarly, in this equation 2, first expression left side fk minus 2. Next, a0 quotient is xk minus 2 square. Next, a1 quotient is xk minus 2, and a2 quotient is 1. Similarly, other two expressions. Okay, now let us eliminate on expanding this determinant, and simplifying, very big one, and simplifying. I am giving the simplifying version, and simplifying, we get, see what is the polynomial we are getting. The polynomial is f of x expression expansion, determinant expansion by using first row and first column. This is how to write this polynomial, how to remember. First you write fk minus 2, and its quotient is a fraction. Fk minus 2, its quotient is a fraction, and the numerator is the differences x minus xk minus 1, x minus xk. Okay, like Lagrange's interpolation formula, right? What is that? First write fk minus 2, and its quotient is a fraction, where numerator terms are the differences x minus xk minus 1, x minus xk, and left remove the difference x minus xk minus 2, x minus xk minus 2 in the numerator, and here in this numerator this x is replaced by xk minus 2 in denominator. That's it, xk minus 2 xk, right? This is the first term. Plus, similarly, if next term is what, fk minus 1, right, fk minus 1, and its quotient is what, here also remove the difference x minus xk minus 1 and write the remaining differences. What is that? X minus xk minus 2, x minus xk, and in the denominator replace this x by xk minus 1. So xk minus 1 minus xk minus 2, xk minus 1 minus xk xk. Okay, and what is the last one? Fk. What is the fk quotient? It is a fraction. Delete the difference x minus xk and write the remaining two differences, x minus xk minus 2, x minus xk minus 1, and replace this x by xk minus xk minus 2 and xk minus xk minus 1. This is the polynomial we are getting after expanding the determinant. Take this as equation 3. Now more complicated one. Now the assumptions are here you have to remember this. Let h equal to here let h equal to x minus xk, the first one, h equal to x minus xk, hk equal to xk minus xk minus 1, and hk minus 1 equal to xk minus 1 minus xk minus 2. To simplify this expression 3, we are assuming h equal to x minus xk and hk value xk minus xk minus 1, hk minus 1 value xk minus 1 minus xk minus 2. And another assumptions, lambda equal to h by hk, lambda, another notation, lambda equal to h by hk, and lambda k equal to hk by hk minus 1, and delta k, this is another notation, this value is 1 plus lambda k, 1 plus lambda k, then 1 plus lambda k, then equation 3 becomes what? Equation 3 becomes h into 3 implies h into h plus hk by hk minus 1 into hk minus 1 plus hk multiplied by fk minus 2 plus the first entire this term reduces to this part. Next one is, next term becomes, this is minus h into h plus hk plus hk minus 1 by hk minus 1 multiplied by fk minus 1 plus third term is h plus hk plus hk minus 1 whole by hk into hk plus hk minus 1 into fk equal to 0. This is equation 4. And if I simplify this equation 4, simplifying equation 4, we get what we are getting. Simplifying equation 4, this is the main equation, lambda square into ck plus lambda into gk plus delta k into fk equal to 0. This is equation 5, where the new notations are what? Where first notation is ck. What is ck? Lambda k into lambda k fk minus 2 minus delta k into fk minus 1 plus fk. This is ck value. Next one, gk value. Gk is lambda k square f k minus 2 delta k square f k minus 1 plus lambda k plus delta k into fk, and fk means f of xk value. Okay, this is the equation 5 is a, what is this equation? Is a quadratic equation, is a quadratic equation in what? In lambda, in lambda. So solving equation 5 for lambda, we get now this lambda value, lambda equal to minus gk plus or minus, it is a quadratic expression applying the formula minus b plus or minus b square minus 4ac gk square minus 4 delta k fk ck whole by 2ck. Now rationalizing this means what? Lambda equal to minus gk plus or minus under root of gk square minus 4 delta k fk ck whole by 2ck multiplied by gk plus or minus under root of gk square minus 4 delta k fk ck whole by the same, multiply divided by same, nothing but gk plus or minus under root of gk square minus 4 delta k fk ck. This is a plus b into a minus b formula. After simplifying, what I am getting, this is minus 2 delta k fk whole by gk plus or minus under root of gk square minus 4 delta k fk ck. Okay, this is the, so what is the lambda value? Lambda equal to minus 2 delta k fk by gk plus or minus under root of gk square minus 4 delta k fk ck, and let it be lambda k plus 1. Lambda is taken as now lambda k plus 1. This is the most important equation you have to remember. Okay, and here I am clearly writing what are these here. What are, you have to remember what is first delta k. What is delta k? 1 plus lambda k, 1 plus lambda k. And what is lambda k? Lambda k equal to hk by hk minus 1, hk by hk minus 1. Okay, next one is what? Fk means f of xk. What is gk value? You have to remember gk equal to lambda k square fk minus 2 minus delta k square fk minus 1 plus lambda k plus delta k into fk. You have to remember this gk value. And what is another one? Ck value you have to remember. This is lambda k into lambda k fk minus 2 minus delta k fk minus 1 plus fk. In equation 6 you have to remember this formula. Okay, now in this for equation 6 plus or minus terms are there, plus or minus. So which sign should be taken care? For that the condition is the sign of denominator, in equation 6 is chosen such that lambda k plus 1 has smallest smallest absolute value, smallest absolute value. Clearly, that is, it has the sign of, simply it has, the denominator has the sign of gk, sign of gk. What is the meaning of this? Lambda should be very very small. Lambda, when lambda is very small, when denominator is very high, right? When denominator is very high, if gk is positive, then I have to consider plus sign here, then more value you will get in denominator. If gk is negative, if I have to consider negative value here, so that the denominator is more than numerator value. That is the logic. Okay, now here what we have already, what is lambda equal to h by hk. We know this, lambda equal to h by hk. And what is lambda? I have taken lambda k plus 1. So lambda k plus 1 equal to h by hk. And what is h assumption previously? X minus xk by, and hk assumption is what? Xk minus xk minus 1. Now this is the value of lambda, lambda equal to this. And now solving this one for x, what I am getting, taking cross multiplication and writing for x, this is lambda into this part denominator, xk minus xk minus 1, and take this minus xk this side, that becomes plus. This is x value, this is x value. Now replacing to get next approximate, actually this is the original formula, replacing x by xk plus 1, xk plus 1, we get, now this is the formula, the Muller's formula for the approximate root, xk plus 1 equal to xk plus lambda into xk minus xk minus 1. This is the Muller's formula, is called Muller method, is called Muller method. And here what is lambda? Here lambda is given by what? Lambda is given by what? Equation 6. Lambda is given by equation 6. So in Muller's method you have to remember this formula, this important formula, and this lambda formula, lambda formula. Now graphical representation of Muller's method. Graphical representation of Muller method. Muller method. See, directly I will explain through a graph. This is x-axis and this is y-axis, right? Let me consider one graph like this. This is the curve. What is this curve? Y equal to f of x curve. This curve is what? This curve is what? Y equal to f of x curve. And this is exact root. The curve cuts the x-axis at the exact root. Okay. Now in Muller's method, what we have to consider? Three approximations. I am taking x0, some x1 here, okay, and some x2 here. Three approximations: xk minus 2, xk minus 1, xk. I am substituting k equal to 2, so roots becomes x0, x1, x2. Now at x0, the point on the curve is this, is the point x0 comma f of x0, and the point on the curve at x1 is this, point on the curve x1 is this, this is x1 comma f1. And similarly the point on the curve, at x2 is x2 comma f2, x2 comma f2. Now join these 3 points, by a curve. Join these 3 points by a curve. This curve I am taking. Join these 3 points by a curve or straight line, okay, which cuts the x-axis at the next approximate root x3. Next approximate root x3. Next one, what is the next one? Next roots are what? x1, x2, x3. At x3, what is the point on the curve? At x3, what is the point on the curve? This point, x3 comma f3. Now which point should be joined? X1, x2 and x3 point should be joined. Okay, to join the curve, now see, somewhat how to join these three curves, your choice. Okay, let me draw the curve in this pattern, joining these three curves like this. This is the next approximate root, x4. This is the next approximate root, x4. Okay, now what are the next roots? X2, x3 and x4. Like that you have to continue. Okay, this is Muller method.